Good day, everyone. So today we'll be talking about charge carrier diffusion. So when we have a concentration gradient, or there is a difference in the concentrations in the different regions of our solids, diffusion may occur. So hindi exempted dito ang ating charge carriers, electrons and holes. So if there is a change or a difference in the concentration between electrons in one region and the other, we'll expect that there will also be diffusion of these electrons, or if holes sila, holes din. From diffusion, we know that our substances would migrate from the higher to lower concentration. So take for example, in this situation, this one. In here, let's say the blue circles represent our electrons. In X1, the region X1, this is of high concentration. Meanwhile, yung sa X2 natin, this is your low concentration. To get from, to go into equilibrium, the tendency of our system is to diffuse from high to low concentration just to balance everything out. So we'll see that there will be a diffusion of our charge carriers from X1 to X2. And due to this diffusion, there will be movement of our charges. And this movement will lead to the production of what we call your diffusion current. So what is diffusion current? Diffusion current, let's just write it here. Diffusion current is the current produced by the diffusion of our charge carriers. It may be electrons or it may be holes. So for example, in here, and for our electrons, there is a diffusion from X1 to X2 of our electrons. So in this case, from Fick's first law of diffusion, the diffusion flux of our electrons, this will be equal to, from your kinetics, negative dn over dx, where dn, this is your diffusivity, and dn over dx is your concentration gradient. So remember n, this is your concentration. This is your concentration of holes. And dx is yung x2 minus x1. This diffusion flux, this electron diffusion flux here, since this is a movement of our charge carriers, we can relate this to our diffusion electron velocity. Your diffusion flux, this one, so this is flux. Your diffusion flux for your electrons, we can express this in terms of our electron velocity, electron diffusion velocity, V E diff, multiplied by the concentration of our electrons, N. Using these two relations, this one and this one, we can combine them and we'll see that VE diff and VE diffusion would then be equal to negative dn over dx. Isolating VE diff in one side, we will get VE diff is equal to negative dn 1 over n dn over dx. This is your velocity of electrons due to diffusion. From here, we can get our diffusion current. Our diffusion current density, let's use a different color. Let's use blue. our diffusion current density is just JE diff. And from your diffusion current, this is just equal to NQV diff VE diffusion. Or this will be equal to negative NQ, sorry, negative NQVE diff, or negative NQ negative dn 1 over n dn over dx. Canceling negative n, we will get GE diffusion is equal to Q dn over dx. So we'll see here that our diffusion current density for our electrons would be dependent on the diffusivity of our electrons and also the concentration gradient of our electrons. Concentration gradient. We can also get a similar expression for our holes. So for holes naman, this is a different color again. For holes, VH diffusion is equal to negative dP 1 over P dN over dx, while yung whole diffusion current density is equal to Q dP over dx. So that is for your diffusion current. Let's now tackle the Einstein relations. The drift and diffusion currents of electrons and holes are connected to one another. Since basically it's just the movement of the same charge carrier, different lang yung stimuli. Yung isa is an applied electric field and the other is a concentration gradient between the charge carriers. So Einstein said that there is a relation basically between this diffusion and drift current, or specifically yung diffusivity and the mobility of our charge carriers. So to look at this, let's consider a material under an electric field E. So let's say we have this material here. We apply an electric field as so. So this will become positive and negative. This electric field will then cause electrons in our material to drift towards the positive side or opposite the direction of our electric field. So we'll produce a drift current. Drift current is produced by your electric field. Due to the drifting of our electrons from the right side to the left side here, we will see that there will be an imbalance in the concentrations between the right side and the left side, because lahat nga ng electrons natin, or most of our electrons, are migrating from the right side to the left side. So we'll see that the concentration of electrons would be higher concentration here than here in the left side. Due to this difference in the gradient or difference in the concentration, kakaroon tayo ng gradient. Will produce a gradient here. High concentration, low concentration. If you have high to low concentration, we will be having diffusion. So your electrons will then counter diffuse opposite of that of the drift current or of the drift velocity of our electrons. So yung electrons mo sumobra na dito, konti na lang dito, kakaroon tayo ng movement of our electrons from the left side, which is high concentration, to the lower concentration region at the right side. At thermal equilibrium, the sum of the drift and diffusion currents, so this is diffusion and drift, must be equal to 0. So, JE drift plus JE diff should be equal to 0. JE drift, or the current density due to drift, is equal to NQ mu EE. While yung diffusion naman natin, the current density, this is equal to Q dn over dx. This relation here, this is actually a first order differential equation. Writing this first order differential equation, dn over dx plus mu EE over dn n is equal to 0. Solving for this one, this will become nx is equal to n naught exponential of negative mu EE over dnx. For non-degenerate semiconductors, this one. So this is, ito yung nakuha natin sa first order differential equation. Meanwhile, for non-degenerate semiconductors, from the Boltzmann statistics, the electron concentration, sabi ni Boltzmann, is nx is equal to n naught exponential of negative QE kBT x. Yeah. So we have now two different equations for nx, or the concentration of our electrons with respect to the position x. If we compare these two equations here, comparing ito and ito, we'll see nx is the same, n naught is the same. Yung exponential nila, magkaiba lang nasa loob, negative QE over kBT. Isa negative mu E over dn. So when we equate these equations, we'll actually get that mu E over dn is equal to, or x is equal to, negative QE over kBT x. Canceling E, canceling x, canceling negative, we'll get that mu E over dn is equal to kBT over, it's equal to Q over kBT. Or, reversing this one, so you see, bigger. Reversing ito. This is actually now our Einstein relation, or dn over mu E is equal to kBT over Q. So this gives us a relationship between the diffusivity and the electron mobility of our electrons. For holes, meron din tayong similar relation. For holes, we can use a similar, we can do the similar analysis, and we'll be given dp over mu h is equal to kBT over Q. This one. At room temperature, the value of kBT we know is 25.9 milli-electron volts, and Q is just 1 electron. So yung kBT over Q natin is just 25.9 millivolts. And this tells you that for a given, let's say, if we know the temperature and we know one of the two of the either diffusivity or the electron mobility, we should be able to get yung other quantity natin. So the Einstein Relations basically gives us a mathematical link between the diffusion and your drift processes. So yeah. Kasi ito naman, this is just dependent, this is a constant is just dependent on the temperature. So it's really useful to have when we're trying to solve problems uh, regarding the movement of our charge carriers. Another important property that we have to consider in the charge carrier diffusion of our materials is the diffusion length of our charge carriers, or our electrons and our holes. This is because our electrons and our holes do not diffuse infinitely into the end of the semiconductor. Magkakaroon ng point in which they will encounter the hole or electron na opposite sa kanila, and they will recombine, and di na sila free, di sila mapag-move. So, let us consider, let's say, a 1D semiconductor, as seen here, where excess concentrations of electrons are injected into x equals 0. So dito ibig sabihin na parang nag-i-inject tayo, linalagyan natin siya ng electrons there. Then these electrons will then be allowed to diffuse towards x to infinity. Kasi nga dito meron tayong concentration gradient, ay mas mataas concentration natin than this one. Kakaroon tayo ng profile that would look something like this. The excess concentration profile, when we graph that with respect to x and delta nx, where delta nx is the number of excess electrons at a specific point x, would look something like this one. The produced excess electrons at x equals 0, while it is diffusing towards x equals infinity, these electrons would experience recombination events. So, pwede siyang makamit ng ibang hole. Pag, kunyari, meron tayong electron plus hole, or electron plus hole, mangyari dyan, magka-cancel each other out. Or if we look at the band diagram, you have your electron here, and you have your hole here. Aba, siya mawala yung charge carrier natin. So, or, pwede rin mangyari is your electron, this can meet with a charged donor atom, D+. So, again, natanggal yung charge. Yung electron mo, hindi na siya makakagalaw. So, these recombination events will then lead to a decrease in the number of excess concentrations as we get away from the injection point x equals 0. There are a lot of different recombination events. Meron, di lang yung dalawa na pinilagay ko dito. But for our purposes, let's just lump them all together. And then we can introduce a characteristic time, tau n. This tau n is what we call the recombination lifetime. Recombination lifetime of our charge carrier. The recombination lifetime is just the average time for a charge carrier to recombine and is related to the recombination rate Rx. Rx would then be equal to delta nx over tau n. Now let's consider the infinitesimal region of space between x. Let's say we have ito, this one and this one. This is x naught, and this is x naught plus dx. So we have electrons here and less electrons here. So let's consider this region here. This region dito. Let's consider this dx region here. Let's say meron kang diffusion from this side towards this side. Ang mangyari dito is from ito, papunta dito, nag-pass through siya this region here, makita natin mas konti na yung electrons mo dito. In that diffusion, during this diffusion, kumonti nga yung electrons natin. Some of the electrons were lost. Some of the free electrons were lost due to the recombination in this region here. So, makita natin that the flux in is greater than the flux out. And if we do a mass balance for this one, we will see that at steady state, yung influx natin yung flux in natin in this region, this one, flux in, will then be equal to yung flux out natin, and kung ano man yung kulang or minsan yung sobra will be due to the recombination, Rx naught here, times yung recombination rate na yan, times yung width nung ating region dito. Since we have expressions for flux in and flux out, pag flux in, this is just yung diffusivity, negative dn, d delta n over dx at x is equal to x naught. Meanwhile, yung flux out natin, this is just the same, plus negative to dn, d delta n dx. Nag-iba lang yung x na kinoconsider natin. X is equal to x naught plus dx. The steady state equation, when we put this one and this one back into this expression, would be negative dn d delta n dx, x is equal to x naught is equal to negative dn d delta n over dx, x is equal to x naught plus dx, plus yung recombination natin, Rx naught dx. We can then get this one. This is we can then get a second order differential equation with respect to x from dito. We will get dn is equal to d squared delta n dx squared is equal to rx, and inserting the expression for rx aling dito, rx delta n, rx equal to delta n x over dn, tau n, delta n x over tau n. We will then get we will then get dn d squared delta n dx squared is equal to delta n x over tau n. We can rewrite this so that yung differential natin is just on one side, d squared delta n dx squared is equal to delta nx tau n dn. From this expression, we can see that yung tau n delta dn natin, tau n dn natin, this will just have the same dimension as distance squared. Tau n is just 1 per second, while dn is just meter squared second. Ito yung units niyan. Canceling, makita natin this is just distance squared. So if this is distance squared, we can actually get the square root of this expression. We have ln, yung square root nito, square root of tau n dn. And this ln here, this is now we define as your diffusion length. So yung diffusion length na yan, this is just basically parang the characteristic length in which your electrons travel before recombining, or the amount of distance distance traveled by an electron or pag hole yung ating charge carrier hole before recombination. Pag holes naman tayo, we just change yung subscript. We have LP is equal to tau P dP. Finally, we can also solve this second order differential equation, and we'll get solution of that one will be equal to delta nx is equal to a exponential of x over ln plus b exponential of negative x over ln, where constants a and b can be obtained from the boundary conditions of our problem, depende sa problem natin. And basically, that's it. So, from here, we can get yung concentration profile ng ating electrons, concentration profile ng ating charge carriers in our system. And a very useful characteristic of that, to get the correct, the concentration profile, is yung ating diffusion lengths. Na ito, and ito. And with that, I will end yung ating charge carrier diffusion part of the video. So thank you for listening and hope you all are having a wonderful day.